Hello, this is our video submission for our final fuzzy logic project. This is part A for the design of a fuzzy logic controller, comparing it to a PID controller. We can start with our fuzzy controller program. You can see here we entered it in from MATLAB, and then we can open it up. So as described by the problem statement, we've got a fuzzy logic controller that's going to have two inputs, our position error and our rotor velocity, and it will output our motor voltage, which will eventually be fed into a transfer function, and then it will give us a final rotor position. So each of our inputs are going to have three membership functions. Each is going to have a Gaussian type, and it's going to have which will have a beginning and an end parameter. The position error is going to be a negative error, a zero error, or a positive error, and that will be reflective for each one of our inputs and also our outputs. So we're going to have three. So one's going to be negative, one's going to be zero, one's going to be positive, all Gaussian, all have a beginning and an ending parameter. You can see that to be true for our second input and our output. We can jump into the rule editor, which can be confirmed with our problem statement, is that we're going to have 9 rules, and then confirmed here we've got 4 negative rules, 4 positive rules, and then 1 zero voltage rule for our output. And one way we checked it was comparing it to our control surface plot, our rule surface plot. And so we can click this, and then we have the same shape as seen in the provided document. Normally, if we were just looking at one point of inputs, we could pull up our rule interface as well, and then plug in each of our inputs. So that was going to be our position error and our rotor velocity, and then we could see what our motor voltage would be at that exact point. As we go into the Simulink, we'll see it'll be a large value of points spread out across from 0 to 30 seconds. And so that wasn't performed right here, but this is what we would be expecting to see. If our inputs were these two numbers, we would be expecting, a motor voltage of essentially 0. So we can move in then to our Simulink. Here we have two areas. We have a fuzzy control and we have a PID control, and they are going to work in similar ways. So here we have our desired position. Our desired position is going to be 1. We have it 1 immediately with no step time, and that is fed through a feedback with our current position. So for our fuzzy logic, we required 2 inputs. One's going to be that position error, the difference between our desired and our current, and that is fed in as our first input here. And then we will also have the derivative of that, which is going to be our rotor velocity. It's going to be, how fast it's changing its current position to reach this desired position. And that is our second input as seen right here. And that gets fed into our fuzzy logic controller. And then the output here is our motor voltage. The motor voltage, as I said before, is fed into a transfer function, which then outputs our current rotor position. So all of that is then sent along with a clock to track the time that each value is given into our 2 workspace block. And so all of my values from this part of the simulation will be saved into a matrix called Y. The PID controller is very similar with the input of 1 and the feedback. And that is our only input into the PID controller. It only needs 1. And the PID controller was auto-tuned using the tune feature. And the motor voltage is our output, which then gets fed into the transfer function. And then we get our rotor position back out. And then to keep things as clean as possible in the code, I made sure that all of the fuzzy logic inputs are going to be in matrix Y, and then all of the PID is going to be in matrix Z. So then we can move into our code. So starting off, this is just clearing anything that might be lingering around from a previous program. This is loading the simulation and performing it. And then we have a bunch of different sections for the deliverables to make our plots. So we've got our plot to confirm our fuzzy controller is controlling to what we want it to be. We've got a comparison and a plot to see our inputs and our output for our fuzzy controller. We've got a comparison of the input signals for each controller, and then we've got our controller output comparisons, and then finally we have the rotor position performance, so we can see what controller is doing well for factors like uh, overshoot, settling time, so on and so forth. What benefits does each controller have, or which ones, or what problems does each controller have? So we can start and just run it. And one thing, so that we know that it is performing or working through this simulation, is so right there. So the loading bar, so that's how we know that this is being ran right now from our MATLAB script. And 30 seconds is a relatively long time with I believe the fixed step is 0.001. But once that gets done, we should have 5 figures that pop up. Yep. So we'll just work through one at a time. So here, our fuzzy controller rotor position. So this is our top plot. And we can see that it is successful. So our desired blue line is our desired position. So that's our 1. And from there, we can see that sorry for opening up Teams, that our actual rotor position from our controller is rising up where it's got a very minimal overshoot, and it essentially just goes straight up to 1, but it takes a relatively long amount of time that we'll see in a future plot. So our second plot that we want to look at is our fuzzy controller inputs and outputs. Our input 1 is our position error. And we can see the max value is going to be 1 because we're going to start off at a current position of 0. And so the difference between our desired 1 and 0 is 1. And then that will decrease as the controller goes to our desired position. And so this behaves as we expect. So our motor voltage is, or I'm sorry, our input 2, our error derivative, this orange line, is also going to behave as we expect because this is our rotor velocity. So it's going to be speeding up from essentially rest up to a peak point. And then once it starts getting closer to our desired position, it begins to slow down until eventually when we reach 1, it'll stop spinning. And so our rotor position will turn off. It'll also be 0. Our motor voltage to essentially drive that velocity is going to once again have a spike and then also decrease as we get to that position. And that is plotted on a separate line because it's on a scale of 6. And so that way it's easier to see all 3 lines, but you can still see, even though there's an offset between them, it's still going to 0 just like the other lines. And so this also confirms the expected behavior we want to see from our fuzzy controller. So plot 3, this is our input signals of both of ours. So we have 2 inputs for our fuzzy controller and 1 input for our PID. Once again, we have our error derivative or our rotor velocity and our position error. And then we have added here our PID input, a position error. You can see from the plot that it actually spikes up like very high. It actually goes past the scale here. There's a artificial limit that I put in. But that spike is a characteristic of PID controllers where just for like an instant, you can see right here, we're at half a second while we're already back down, but it'll have an initial extreme spike for our position error as it tries to fix its, as the PID controller kind of activates and starts trying to fix the discrepancy between our desired position and our current position. But as that position corrects itself, you can see it start going to 0, just like the other inputs. So that is what we expect and what we want to see. Figure 4 is going to be our controller output. So once again, that's our motor voltage seen here and seen here. And our motor voltage, the PID controller, we'll see later on, will have a more significant spike and to correct itself. And so it will bottom out to 0 faster than the fuzzy controller will. And we can see and compare, once again, reflective of that spike. We'll expect a pretty significant dip. And then this part right here is more of what we are going to be seeing. right here on the orange line. Finally, this is our performance. So both of these are driving our rotor to be at the position that we want it to be. So in blue, we have our fuzzy controller performance that we've seen before. So this is the essentially the time it's taking and the path it's taking to go from a position of 0 to a position of 1. Our PID controller, you can see, has a significant overshoot compared to our fuzzy controller. But the trade-off for that is our PID controller is going to essentially get to our desired input at, I mean, you could argue that even at this point, it would be fine at 1.009 for desired of 1. And so that's occurring at 6 seconds. Whereas our fuzzy controller is going to achieve that around the 14-second mark. So we have about an 8-second difference. And obviously, one isn't necessarily better than the other because you could design something like a chemical vat tank. If you design it to where it's got enough overhead to where a little bit of overshoot isn't going to make any of the content spill out, and you desire to have your process running faster, then a PID controller could achieve what you're looking for it to do. Whereas if, let's say, you're constrained and you can't overfill a container at all, then a fuzzy controller, you take your extra time to make sure that your overshoot doesn't spill any of its contents, and then that would be a better system for what you want. Either way, both of these systems seem to be performing how we would expect, where our fuzzy controller is a little bit slower, but not as much overshoot, and our PID controller is able to correct much faster with a relatively more egregious overshoot.